In this project, I built a supervised learning model to predict the hourly electrical power output of a combined cycle power plant. The target variable is net electrical power output, and the input features are ambient temperature, exhaust vacuum, ambient pressure, and relative humidity. The output is a continuous numerical value, and that suggests this is a regression problem. Before building any model, I first explored the data visually. Here I'm showing a scatter plot of temperature versus power output. We can clearly see a strong negative relationship. As ambient temperature increases, power output decreases. This confirms that temperature is a meaningful predictor. To evaluate the model properly, I decided to split the data into 3 separate sets. First, I generated random values. Then I copied and pasted only values from the column F in order to freeze the data. Next step was assigning approximately 60% of the data to training, 20% to validation, and 20% to testing. The training set is used to fit the model, the validation set is used to compare models, and the test set is reserved for the final performance evaluation. I started with a baseline multiple linear regression model trained on the training set. In this model, power output is a linear function of temperature, exhaust vacuum, ambient pressure, and relative humidity. The regression achieves an R-squared of about 0.93, meaning the model explains most of the variation in power output. The strongest coefficient is temperature, where each 1 degree increase results in nearly a 2 megawatt decrease in output. Using the coefficients from the training data, I generated predictions for the validation set. I evaluated model performance using RMSE, or root mean squared error, which measures the typical prediction error in megawatts. First, for each observation, I calculated the prediction error as the difference between the actual power output and the model's predicted value. Next, I squared these errors to remove the sign and emphasize larger deviations. I then averaged the squared errors across all validation observations and finally took the square root of that average to obtain the RMSE. RMSE is appropriate here because the target is continuous and errors should be penalized more heavily when they are large. The resulting RMSE on the validation set is just under 5 megawatts, which indicates that the model's predictions are typically within a few megawatts of the actual measured power output. Given that the plant operates in a range of over 400 megawatts, this represents a relatively small error and suggests the model performs well. To improve the initial model, a simple nonlinear feature was introduced by adding a squared temperature term. The next step was to retrain the multiple linear regression model using the same training data, now including this additional feature to allow for nonlinear effects of temperature on power output. For a fair and consistent comparison, the same transformation was applied to the validation data, and new predictions were generated using the updated model coefficients. Model performance was then evaluated on the validation set using RMSE and directly compared with a baseline model. The enhanced model achieved a lower validation error, indicating improved predictive performance, and therefore I would select this model as my final one.